Log on, tune in, find out. Another good idea from Cambridge.
So, well, I think let's start with the second presentation by Mr. Correia. And now, well, it seems to be more academic. It's about nonlinear hyperbolic conservation laws, diffusive-dispersive limits, and what is meant by this we will learn in a moment. Please.
Okay. Good morning. Thanks. First of all, I need to express how happy I feel to be here at FINI for my second time, and deeply thanks the great welcome. Secondly, I must apologize for my very bad English, perhaps a bit better after this week with you. Okay, welcome to my talk. Okay, why diffusive-dispersive limits? While diffusion has a dissipative effect, dispersion has an oscillatory one, which brings us back, of course, to the conference theme, Ike oscillations. I can give you a visual idea. Oops. But this is not a good idea because I will be guilty of the laptop pain. Instead, perhaps I can see that in the eyes of some of you, I detect a few people addicted to ABS brakes. You know, often these does not end well. Okay, let's try better. Unfortunately, the workshop ends, and today most of us will fly. Feel the oscillations. That seems stop. But this is just because the frequency goes up, rise to the point where the wings, okay? Okay, where we are concerned with shock waves, discontinuities. Oops. If you are interested in mathematical applications to the industry for these sort of things, a 3 hours lecture, of Swazwa is a very interesting lecture. Okay. Of course, in these applications, oscillations is a bad thing if you want to have optimal design, dynamic control in structures. But perhaps to control them, we can have some device to detect, prevent these oscillations based on phase transitions, properties of martensitic-like materials. The point is that for similar equations in actually concerning these two issues, We can have similar equations, but their solutions are unlike. The idea is to have extension of the celebrated vanishing viscosity method. In footnotes, I give some reference. Okay. To be more specific, let me restart my introduction. Take the point of the common other. Maths is a tool. Equations must be so simple as possible. So, if a problem, an equation cannot be linear, at least that it can be of first order. This can be done discarding spurious small terms as viscosity in the Burgers equations, which actually converge as a first example of vanishing viscosity method. But if we are concerned with KdV equation, we can these don't not converge in the sense that the solutions do not converge to the hyperbolic ones. So we have a problem. Okay, Schoenbeck has been the pioneer work using Tartar setting on compensated compactness, and she proves convergence in a diffusive Of course, to have convergence, we need that diffusion dominates dispersion. Okay. The setting of Schoenbeck was this equation, which is one-dimensional with convex flux. The solution is not forcibly the entropic one, and she was restricted by specific and restricted Lebesgue space and flux growths. Then, using the Dipernus setting on Young measures, Le Floch and Natalini applied to such things, sort of equation, also with a linear diffusion, but the main case is with a nonlinear diffusion. They don't need convex flux, and they have the entropy solution. But because their energy estimates are the same of Schoenbeck, restrictions with specific and restricted Lebesgue space and flux growth are the same. Okay. The point here is that we'll have a sort of paradox. Okay. For the first time in my paper with Lovelock, I take the multidimensional at the other integrity region. That means we have classical entropy solutions, and over these lines we went in some parts have non-classical entropy solutions. This depends on the balance gamma between diffusion and dispersion, and growth ratio, which is the for us the best issue to understand the whole of diffusion and dispersion. Okay, we look to our physical solutions. We are aiming to a multi-space dimension, if possible realistic, using Young measures, energy methods, without dimensional arguments just now. And the assumptions we need are in fact very light ones: growth, which are needed in the Young set analysis, and potential. In the case of Korteweg de Vries, in fact, we only need the existence of potential. Okay, coercivity assumptions. The usual diffusion assumption, say monotonic, dissipative, linear, generalization of linear operators, and these assumptions about the dispersion for the case we are concerned here. Okay, the first theorem concerning the KdV-Burgos equation as this ratio. We have, due to the Perna setting, here a problem with little o, but in this paper, which arrived after a first paper by Zavaras, also with Wang, which use kinetic approach, and by this approach we can have here a big O. I'm not understand, in fact, if this is a very nice, sharp balance. Because they have the bigger O. In any case, in some particular case, we can see that the optimal, the sharp balance is in fact given by this relation. This result, we are no more constrained by specific Lebesgue space, and we can handle any flux with any ground. Concerning the generalized Benjamin-Bohner-Mahoney Burgers equations, to explore all the possibilities for the flux growth, I need take 5 parts of the older line. Here I give you one example. Here the energy estimates are very big, difficult, so we are once more constrained by fixed Lebesgue space. R and M means that this Lebesgue space depends on the growth of diffusion and the flux. So once more, in this case, flux, dispersion, and diffusion interact. This is not the case here. Of course, this must be because we have, in fact, diffusion regime that dominates strongly the dispersion, and in the low regime, I suppose we need to take tricks on dimensional arguments. Okay, I am working on Bernier conjecture. Okay, of course, main issues are about failure, integrity, sharpness of these regions, and reliability concerning, in particular, non-classical solutions, low ratio growths, and of course I look, I try have some nice physical models. In fact, I can capture linear models, nonlinear, like Neumann's pseudo-viscosity or the P gradient, P Laplacian, sorry. But concerning dispersion, I don't have nice suggestions. So, if you have some suggestions, please, and thank you very much for your attention. Sorry. So now, please feel free to ask questions.
This mathematical topic. So then let me start. You had this coefficient gamma that related diffusion and dispersion. So what you have done was playing with mathematics, and you investigated all these different cases. But in nature, there's often some universality principle, some scaling law that somehow fixes such coefficients to particular values. So, well, probably you don't know, but are there such universal coefficients that relate diffusion and dispersion in physically relevant models? Is there any insight?
Yes, in fact, I know some papers, but in fact, I try to understand and in fact classify.
Mm-hmm. Yes, this is the mathematics, but now you had in red this item physical models, and this would be a very important question, whether you have to look at all possible gammas or maybe nature as a preferred choice for such gammas, so that certain regimes never occur in meaningful models. So this is an interesting question for a modeler or a physicist, probably.
Yes, I went for.
Mm-hmm. Any other questions or remarks? Not the case, then let's thank Mr. Correia again.